I'm going to start sharing my screen. And I'm going to start with the notebook that I'm going to be writing the notes on, because I have a couple of announcements here. Today's January 26th. We're going to, again, be working on that unit that involves sets. Today, we're going to be looking at the idea of cardinality, different types of subsets. And if my internet holds out, again, I apologize for all the times that my internet dropped me last week. The last thing I did before class started was reboot the router, so hopefully that helps, right? If time and internet holds out, we'll also start looking a little bit at Venn diagrams. Homework 1 and 2 will be due next week. I think I wrote down here the 2nd, which is the day of class, but actually I think in my labs it says that it's due the 3rd. The next 2 homeworks will be due the following week on the 9th. Next week, we're going to meet that F2F is my lazy way of writing face-to-face. Next week, if all holds well, we'll be meeting on campus in B114. I don't know how familiar with campus any of you are. B114 is the lecture hall on the 1st floor of B building. COVID rules, when you get there, please space out. As much as I know it's great fun to sit right next to somebody in class and you know, share class with them and work together with them. At this stage of the game, in order to be on campus, we're going to socially distance. I am hoping that there will be a way for me to record the classes. Previous semesters when I taught on campus, I always used a smart pen, which recorded the audio and the written word, and it gave you an option as how you looked at it. Later this week, I haven't taught in that lecture hall in a while. Later this week, I'm going to go on campus and meet with OIT and see if there's a way of, in case people can't make it to campus, continuing with the broadcasting the class on Zoom or something like that and recording the class. I won't know how that goes until after I meet with them on Thursday. I'm sorry. Yes, I'm meeting with them on Thursday. Next Tuesday, there will be a quiz and it'll be on the content covered in homework 1 and 2. Before we take the quiz, I'll answer any questions that you have on that. Because we'll be meeting on campus, it'll be a pencil and paper quiz with questions that I've written in the past. So it won't be a My Math Lab quiz. Before class started, I was having a cup of soup with my husband, and my daughter called, she portaled us with her baby, and we were talking about snow days. And that brought up a question in my mind. So I'm going to stop sharing my screen for a minute and look at you guys. Well, there's not a lot of you to look at, but looking at you guys, I'm wondering, do we want to come up with, before we move on campus, some sort of agreement with respect to what we're going to do if weather goes south? Well, not south, north, I guess. Weather goes Arctic, tropical. Today, I don't know, I didn't go too far into Niagara County. I only went to Tonawanda where my daughter lives. Do any of you live near campus? How bad was the weather out that way today? Do we need to come up with some sort of our own rules in terms of whether the weather's bad, or should we just leave it to, if the college cancels class, we'll cancel class, but if class is canceled, as long as I know about it enough in advance, I'll try to still hold a meeting on Zoom. Does that sound all right? That if we get us, heaven forbid, the college closes because of a snow day, I'll send out a link and we'll still try to meet on Zoom. Is that all right, folks?
Yep.
Yes.
Okay.
Yes.
All right. And we'll leave it up to the college whether they cancel class or not. Then I'm going to go back to that screen that I was sharing. I'd like to pick up with where we left off on the notes. But before we do that, I'm going to be an old person and go back into Blackboard and show you a couple of changes that I made. That link for class will be this class that we will use for link all along. However, if anybody wants to meet outside of class time, during my office hours, or if we can email and come up with a time other than office hours. Can everybody look over here at my screen in Blackboard as I go down this toolbar on the left? I added in the section that's course syllabus, course schedule, learning modules, my labs, my grades. Does everybody see below that where it says office hour Monday, Wednesday, Friday at 9 and Tuesday, Thursday at 11? If you click on that, that Zoom meeting for my office hour will immediately open up. And so that the Zoom meeting for my office hour is there. Also, going back up a little bit in course announcements, I put in 2 announcements today. One is that Zoom class link. It will be there if we ever meet in Zoom again after, but also down below, there's another one about tutoring. We got a message, the faculty got a message yesterday, and I'm not positive if all of you students got it in an email, but the Academic Center for Excellence, the ACE, is starting one-on-one tutoring. After February 1st, they will have face-to-face tutoring on campus. They will also have, starting now, and also after February 1st, if people don't want to be on campus, one-on-one tutoring. If you click that link, that first link that I have there, it will take you to where you can sign up to schedule regular appointments with a tutor if you'd like. If you aren't comfortable doing that, you can either call the phone number here or click the link here and message people about how you can get tutoring. I think they will also have some drop-in tutoring if people don't feel like you need to make an appointment and meet with somebody every week, but you need help with class that you're not getting from the My Labs, and if you're not able to meet with me. Again, if you want to meet with me before you go to the ACE for tutoring, I'm perfectly fine with that. We can set up meetings through Zoom. Any questions on any of that? Next thing I want to do then before we get started is I want to go into My Labs. And when I looked this morning, it looked like an awful lot of you had not yet registered for My Labs. When you click the link for My Labs, you'll first get a screen like this. After that, if you click on any of the links, it'll take you to that Make an Account and Register page. Again, if you're waiting on financial aid, or if you're waiting on somebody else getting a paycheck or something like that, there's a place where you can get that 14-day free trial. I think I showed it to you last week. Does anybody need to see where that option is again? Because I can see if possibly I made a fake class today, see if possibly I can reach that page through the fake class. Do you guys remember where that 14-day free trial is? Or did you want me to try to show you again?
You show us again.
Okay, then let's see. I am going to back out of here. And a course that had originally been in my Blackboard, but wasn't carried. I'm going to go to that class. And oops, I take that back. I need to go in with student view first. So this course that wasn't carried, I'm going to go to the My Labs link. Then I'm going to click on the course home, and it's going to come up with, I don't get that screen to create an account because I've created so many accounts that Pearson's probably mad at me. So the first screen you're going to get is going to ask you to create an account. It's going to ask you to put in your name and address and phone number and an email address. Make sure you put in a good email address, because if you ask me a question, that's where the response will go. And it's going to ask you, then it's going to take you to this screen to register for class. If you've bought an access code through the bookstore, you're going to over here where the pretty colored folders are, you're going to open your pretty colored folder and click that access code and type in the code that you have. If you don't, again, this is a different class. You'll have two options here. I would strongly recommend, if you're going to buy it right from Pearson online, that you take the less expensive option, the 1 semester option, because this is a 1 semester course. But then down below, do you see over here down below where all that fine print is? It says waiting for financial aid, get temporary access without payment for 14 days. It doesn't look it, but that blue get temporary access without payment for 14 days is a link. And if you click on that link, it'll ask you if you really want temporary access, click yes, and it'll take you right into class. And so, so if you're going to use that temporary access, once you get to this screen, it's that blue part of the sentence down below. Everybody all right with that?
Yes.
If so, then I'm going to get out of this fake class and get into your actual class. And in your actual class, I'm going to go into that My Labs and ask, is there anybody who did get into My Labs and started doing any of that first assignment that has any questions about that homework? Does anybody have any questions on it? Any questions? And I promise I'll start every class asking that. If anybody has anything from the homework they want to go over. Go ahead.
I didn't finish it because obviously we didn't learn all the information that's on the homework.
Right.
So what does the homework encompass? How many classes? Is it like the first 2, or is it like 2 classes per homework, or?
It varies from section to section. I had actually hoped that first class that we would have gotten through the first 2 assignments, because since this is a class that meets once a week for 3 hours, in theory, in that 3 hours, we're supposed to cover what would be a week's worth of content in a class that meets Monday, Wednesday, Friday. However, because of the internet problems that I had, we didn't get that far. So some homework assignments will just be, 1 class. I'm hoping that in each class we'll cover about 2 homework assignments worth, because usually with my classes that meet 3 days a week, over the 3 days, there's usually 2 homeworks. Again, we didn't get, and I don't know if you remember, I pushed back due dates after last class because of the fact that we didn't get quite as far. And I promise I will do that. I will reassess where we are at the end of class and let you know if there's any changes in the dates of when things are due. But if you look, most due dates I have, 2 assignments are due. So hopefully we'll be on a pace to cover about 2 assignments, 2 sections of the chapter every week. That's my goal. Okay?
Okay. Thank you.
Okay, thank you for asking. Did anybody want to look at any specific homework questions? I'm going to take that as a no. And so let's get started from where we had left off. If I remember correctly, last class, we took a little bit of time to define a set, saying it's a well-defined collection of objects. And if you started that homework, there are several questions that are kind of just asking, is this a set? Saying, is it well-defined? We went over what it meant to list a set by roster, which was to put all the elements in braces with commas in between, but don't repeat the elements. And we looked at set builder notation, where we used a variable to represent what was in the set. After we did that, we talked about what the empty set is, and we had said that the empty set is a set that has no elements, and we show that in roster by showing braces with no elements in it, or we can use that 0 with a slash through it, which is a symbol for what's called the null set, which is just another name for the empty set. Does everybody remember getting there?
Yes.
Okay. Then next place that we're going to go, next term that we're going to define is that of the cardinality of a set. And I have to apologize. Somewhere along the lines, I'm not real tall, so I go on the assumption that I never grew up. And when I first look at things, I think I have a little kid perspective. When I talk about cardinality of a set, when I talk about the cardinal number of a set, I'm not talking about pretty red birds. No, that's not the type of cardinal that I mean. In some resources, the set of natural numbers is considered like the set of cardinal numbers. There are counting numbers. When I talk about the cardinal number of a set, what it is the number of elements in the set. So when I talk about the cardinality of a set, it's a number, and it's the number of elements in the set. There's notation for that. Oh, I misspelled notation, sorry. Does that look better? Notation, if S is the set, we write a lowercase n, and then in parentheses, we put S, and this means the cardinality of the set. And when I look at this notation, the fact that it's a lowercase n helps me remember that the cardinality of a set is a n word. It's the number of elements. And again, when I talk about cardinality, it is just a number. It's a plain old number. We're not going to put it in braces or parentheses or anything else like that. We're just going to write the numbers. So if we look at a few examples, let's say that D is the set of days of the week. And so I've got the set that we've defined by a description. If I put that notation, n of D, that's saying the cardinality of D, or it's asking the number of elements in set D. So can anybody help me out here? How many elements are in the set that gives me the days of the week?
7.
7. Thank you. Great. Another example, let's say A is the set of letters in the alphabet. What's the cardinality of A? Offhand, can anybody remember how many? Pardon?
26.
Beautiful, 26. Great, thank you. Let's say C is the set C, comma, A, comma, T. What's the cardinality of C? How many things are in there?
What?
How many elements do we have listed? 3.
3.
3.
We have that comma in between. Instead, if I have D as the set DOG with no comma, is everybody all right? The cardinality of that is 1 because it contains one word. Last example, Um, let's say L is the set of all X such that X is a letter in the word letter. And with this one, I want to be careful. It's written in set builder notation. With ones like this, sometimes I like to go through and list them by roster. What are the letters in the word letter? L, E, T. Now, does everybody remember there's a second T in that word, but when we're talking about a set, we only list it once. So I'm only going to put one T in there. Likewise, there's the second E in the word letter, but again, when I list it in a set, elements of the set only get put in once. So I'm not going to put the second E in there. So the last letter is R. And so things that repeat only get counted once. And so for the cardinality of that set, does everybody see that it would be 4? I'm not counting any letters twice, even if they occur twice in the word. That one, all right. Remember that things don't count twice. Any questions on cardinality? Are we okay with that? Not hearing any concerns, can I assume everybody's all right?
Yes.
Okay, then next page. Next thing we're going to define are equal sets. And in terms of equal sets, sets are equal if they have exactly the same elements. Sets are equal if they have the same elements. And I hope nobody thinks that my first example is too irrelevant. Irrelevant isn't the right word. Disrespectful. Let's say D is the set D, comma, O, comma, G. So D is the set of the letters in the word dog. Let's say G is the set G, comma, O, comma, D. The set of letters in the word God. Does D equal G? Do those two sets have exactly the same elements?
Yeah.
I'm getting some yeses and some no's.
I'm just kidding. I'm just kidding. I'm sorry. It's fine.
Okay, you sure? Because order doesn't matter.
No, it makes perfect sense. You're good.
Okay, the order does not matter. But I don't mean for anybody to go out and worship a dog. Let's say C is the set C, A, T with commas in between. And let's say K is the set cat, C-A-T, no commas in between. Does the set C equal the set K?
No.
No. Beautiful. They're not equal because this first set contains 3 letters and this second set contains 1 word. Be very careful. Those commas in between make a big difference between a set with just letters in it and a set with a word in it. Everybody all right with that one?
Yes.
So to tell if 2 sets are equal, we're just looking, do they have the
Yes.
same elements? Beautiful. Thank you, guys.
Thank you.
Next thing we're going to look at are our equivalent sets. And this is some place where you have to be careful. I know in normal everyday discussion, people might use the words equal and equivalent almost interchangeably. And in some places they are the same, but in sets they are different. Equivalent sets are different than equal sets. And equivalent sets has a long, wordy, mathematical definition. We're going to say that two sets are equivalent if there exists a one-to-one correspondence between their elements. Two sets will be called equivalent if there exists a one-to-one correspondence between their elements. To say that it exists means there's at least one. To say there's a one-to-one correspondence means we can take every element of the first set and pair it with a different element in the second set, so that every element of the first set has a partner in the second set. Every element of the second set has a partner in the first set, and there's no doubling up. So what the hell is that all about? Let's look at that set D, which was D, O, G. And let's look at that set C, which is C, A, T. If I wanted to build a one-to-one correspondence between those two sets, I'd take each element of the first set and pair it with an element of the second set. So let's say I'm pairing the D with the C. Then couldn't I pair the O with the A? And couldn't I pair the G with the T? And now is everybody paired off? Is every element of the first set got a mate in the second set? Does every element in the second set have somebody that goes with them in the first set?
Yeah.
There's no leftover element?
No.
No. And so that means there's a one-to-one correspondence that exists between them. But you can go through and you can make this correspondence. If you've got sets like these, let's look at what's the cardinality of D? I think we said it was 3. What's the cardinality of C? It's also 3. It makes that sense that with sets like these, we'll be able to match them up if they have the same cardinality. So we're going to say that if two sets have the same cardinality, they are equivalent. But if I say they're equivalent, is that the same as saying that D is equal to C? No, they have totally different elements. And so I have to be able to match those elements up. If my set end, or if I can count the elements in my sets, if they have the same cardinality, I should be able to make that correspondence. Everybody with me so far? So I'm going to come back to this idea again in a minute. But first I want to talk about something else that's a finite set. And we're going to say that a set is finite
You okay?
if, could everybody please mute if you're not talking to the folks in class because there's some background noise. We're going to say a set is finite if its cardinality is a natural number. And to say its cardinality is a natural number, it means that we can count the elements and eventually stop. So let's say, for example, I have A is the set of all X such that X is less than or equal to 1,000, and X is a natural number. Is that set finite? Can I count the numbers, natural numbers, less than or equal to 1,000? Yes, there's 1,000 of them. Instead, if I have B is the set of all X such that X is greater than 1,000 and X is a natural number, can I count all the numbers greater than 1,000? Is there a largest number greater than 1,000, or do they keep on going and going and going and going and going? This would be a no, because they do keep on going. There isn't a largest number. And so we'll call that an infinite set. And an infinite set is a set that's not finite. One last example that some people have a hard time wrapping their minds around, but I know that it exists as a question in the textbook. And honestly, I can't remember if I put this question in the homework or not, so let's talk about it. Let's say S is the set of grains of sand on, let's name a beach. Let's say Hoover Beach. And here, I'm not going to think about erosion or you know, water coming in and out and moving the sand around. I'm saying if I stop the beach at one instant in time, there's a heck of a lot of sand there. But in theory, we should be able to count it. And so this example would be finite. It's a very, very, very large number, and it would take a very, very, very long time to count. But it would be finite. So with that, I'd like to go back and look up above at where we had talked about equivalent sets and look at two sets that are infinite. So can infinite sets be equivalent? And so I'd like to look at two sets. The first set, let's have E be the set of even natural numbers. And so if I start listing them, does everybody remember natural numbers means I'm only working with positive numbers. So I'm going to start with 2, 4, 6, 8, And it's an infinite set. It'll go on and on and on and on. And I want to compare that to n, which is the set of our natural numbers, our counting numbers that start 1, 2, 3, 4. And it goes on and on and on and on. And if I compare these two sets, are they equivalent? I can't really compare the number of elements because neither of them has a number of elements. They both go on forever. They're infinite. At first glance, you might think, well, the natural numbers are twice as big because they're not just the even numbers, but they're also the odd numbers. But if I take that idea, can I pair each natural number with an even number? Can I pair each natural number with its double? And if I go through and look at that pairing, no matter what natural number I have, won't it have a double that's an even number? And no matter what even number I have, won't it pair with a natural number that's half its size? And so I can make this one-to-one correspondence. And so since there's a one-to-one correspondence, they're equivalent. And that's why we need that long drawn out definition of matching elements in that one-to-one correspondence, because I'm not going to worry about it too much in this class. But if any of you get really interested in sets, you can take the sets classes on Boolean algebra, which is just like a whole semester of nothing but sets. And you start talking about different types of infinity and whether, infinite sets are equivalent or not. And so that's why we need that long, drawn out one-to-one correspondence type of definition. So that if we're comparing finite sets, we know they'll be equivalent if they have the same cardinality. But if we're comparing infinite sets, we have to see if we can match up one element of one to an element of two. Okie dokie?
Yes.
Now, I know one of you had said that you had started looking at that first homework and there were some things that we had not yet covered. I think now we've covered everything in that first assignment. So that homework 1, section 2.1, you should be able to do all of those questions. As you're looking at that homework, if you have any issues, use that question help in the upper right-hand corner. And if that help isn't enough for you, please feel free to use that email my instructor to send me a question. Also, please feel free to drop in on my office hours if you have questions. Stopping just for a minute to take a breath. Does anybody, after we finish this, want to go look at any of those homework questions, or are we good right now?
Okay.
Okay. And again, this homework 1 is called section 2.1 because if you're looking in their virtual textbook, pardon me, it's chapter 2, section 1. If this is all right, I'd like to go on then to section 2.2. And section 2.2 deals with subsets. And in that first section, we're looking at what is a set. How can we see what's inside a set? How can we write what's inside a set? Can we count how many things are in there? Do two sets have exactly the same elements or not? And we're comparing elements to the set that contains them. When we look at subsets, we start looking at two sets and comparing two sets. And so to define a subset, I'm going to say that if A and B are both sets, And whoops, if every element in set A is also in set B, is also an element of set B, we say A is a subset of B. And there's a special notation for that. But again, if A is a subset of B, we're saying that everything inside of set A is also inside of set B. For example, if I said we had the set of students in class, and I could have another set, that's the set of men in class, we would be able to say that the men in class is a subset of the students in class. Every man in class is also a student in class. Let's look at the notation and then let's go back and look at that example. To say that A is a subset of B, we'll say that A, and the symbol for subset is kind of this funny looking C, but then it has a line underneath it. And so that this symbol means subset. And everything in the first set must be in the second set. The fact that it looks like a C makes me think, okay, that means that A is contained in B. Everything in A is contained in B. So every element of A is contained in B. And then when I look at that little line underneath, I'm going to do a little bit of scrapbook that I'm going to erase. That little line underneath almost reminds me of that little line underneath less than or equal to. And when we talked about that less than or equal to, we said it was all right if it was less than, but it was also all right if the two sets are equal. And so that's what this notation means. Every element of A is contained in B, and it's okay if the sets are equal. And so when we're using that subset notation, what we're actually doing is comparing two sets. And so I'd like to make a list of 5 sets to compare. I'm going to have set A be the set C, comma, A, comma, R. I'm going to have set B be the set C, comma, A, comma, R, comma, T. I'm going to have set C be the set A, comma, R, comma, T. I'm going to have set D be the set T, comma, A, comma, R. And I'm going to have set E be that empty set, the set with nothing in it. And so I'd like to try to compare these sets using that subset notation. Would A be a subset of B? Does every element in set A, the C, the A, and the R, are they also elements of set B? Any ideas?
Yes.
Yes, beautiful. So it is a subset.
Yes.
Can I reverse that though? Is every element of set B also in set A?
No.
No. And so be careful with that subset symbol. Order matters. Everything in the one in front has to be contained in the one in back. Is set C a subset of set B? And oh, by the way, I wrote it,
Yes.
I said it, and I didn't make note of it. Is everybody okay if I cross out the subset symbol? It means that it's not a subset. And yeah, this is true. Yes, it is a subset. Is C a subset of A? Is every element of set C also in set A?
No.
Is C a
Yeah.
subset of D? Let's see.
Yes.
Yes, every letter in C is also in D. Is D a subset of C? Is every letter in set D also in set C?
Yes.
Yes. And as I compare those two sets, since they're both subsets of each other, could I say that C is equal to D? Do they have exactly the same elements?
Yes.
Yeah. Great. Now, I want to look at these two where we said it was not a subset. We said that B is not a subset of A, and it was because it had that extra letter T in it, right? B had a T, but A did not. We could say that C is not a subset of A for the same reason. It has that extra letter in it. C has that one letter in it that's not in A. So does it make sense? If it's not going to be a subset, it's got to have extra stuff in it that's not in the other set. Make sense? So is E a subset of A? Is the empty set a subset of my set A, my set CAI? What do you think? Any ideas?
I'm sorry, can you repeat the question?
Is set E a subset of set A? Is the empty set a subset of my set A?
No.
Why not?
It's an empty set. It's not the same element.
Does the empty set have any elements in it that are not in A?
No, they don't have any elements in the E at all.
There's no elements of E at all. So that means there's no extra elements. It doesn't contain more than A. And so this is going to be true. And we're going to say that the empty set is a subset of every set.
Okay.
Because if there's nothing in there, it has no extra elements. Again, over here, this was not a subset. E was not a subset of A because there was that extra element T. C was not a subset of A because there was that extra element T. In order to not be a subset, it has to have an extra element that's not in the other set. And since the empty set doesn't have anything in it, it can't have any extra elements. So it's going to be a subset of every set. How cool is that? That's one that sometimes people have a little bit of a hard time wrapping their minds around. But again, if it's not a subset, it's got to have more stuff in it. And if it's empty, there isn't more stuff in it, so it will be a subset. So I'm going to turn the page and look at a couple more examples. Next example, let's have L be the letters of the alphabet. A, B, C, D, and I'm going to do my ellipsis X, Y, Z. I'm including the whole alphabet. I'm going to have V be the vowels in the alphabet. So that'll be A, E, I, O, and U. I'm not going to do it sometimes. So in class, if we're talking about, or if on a test or quiz, if I'm talking about the vowels, I'm not including that sometimes. Why? The vowels will just be A, E, I, O, and U. And let's have C be the set of all C, such that C is a consonant in the alphabet. Is everybody familiar? The consonants are the letters that are not vowels. That would be like B, C, D, F, G, H, J, K, L, M, N, P, Q, R, S, T, V, W, X, Y, Z, the letters that are not vowels. Is V a subset of L?
Yes.
Beautiful. Is L a subset of V?
No.
Is C a subset of L?
Yes.
Is C a subset of V?
No.
Is C a subset of C? Are all the consonants consonants?
C.
Yep. Because that little line's underneath, it's okay if they're equal. So any set will be a subset of itself. Is the empty set a subset of V?
Yes.
Yep, empty set is a subset of everything. Next one's a little dicey. Is the letter A a subset of V?
Yes.
A is in V. We can say that A is an element of V. But when I have A there standing so sadly all alone by itself, you see that over here, A written as it, just the letter A is not a set. It's an element, but it's not a set. So it cannot be a subset, because in order to be a subset, it has to be a set. Instead, had I written it that A in braces is a subset of V, then this is okay, because here I'm comparing two sets. And if we're using that subset symbol, we have to be comparing two sets. Are you all right? I can say that A is in V, it's an element of V. But that stand alone A is not a set, it's an element. Everybody all right with the difference between comparing two sets with the subset symbol as opposed to comparing a thing in a set, an element with that element symbol? Everybody all right? It's kind of a fine difference. But if I'm using the subset symbol, it's got to be a set.
All right, so.
Then if we're all right with subsets, there's a separate type of subset, and that's a proper subset. We're going to say that A is a proper subset of B if there are two criteria that have to hold. A is a subset of B but A is not equal to B. That should be an uppercase A, I apologize. And so if it's a proper subset, it's a subset, but it's not equal. And so when I look at the symbol for a proper subset, remember when we talked about the symbol for subset initially, we said we can look at that C as saying it's contained in there, and that line underneath, let me erase that because I just made that look like gibberish. The C means it's contained, and the line underneath it is okay if they're equal. And with plain old subsets, it's okay if they're equal. With the proper subset, it's going to be contained, but they can't be equal. And so it's not going to have that line underneath. Let's say A is a proper subset of B. And so, for examples, let's say that S is the set S, T, A, R. Let's say A is the set A, R, T. Let's say R is the set R, A, T. And let's again say that E is the empty set. Off here to the side, I can say that A is a subset of S because everything inside of set A is inside of set S. I've got the A, I've got the R, I've got the T. But those two sets are not the same. So I can say that A is a proper subset of B. No, not B. Hello. A is a proper subset of S. I can say that R is a subset of A because everything in R is an A. But they have exactly the same elements. So R is equal to A. And since they're equal, R is not a proper subset of A. E is a subset of any one of those. I can say E is a subset of A. For that matter, I could say E is a subset of itself. But because any set is equal to itself, E will not be a proper subset of itself. So E is a proper subset of every set except the empty set, pardon me, is a proper subset of every set except the empty set. So does this example help you folks wrap your minds around the difference between what it means to be a subset versus what it means to be a proper subset? If it's proper, they're all in there, but the two sets are not the same. But if the two sets are the same, it can be a plain old subset, but it's not a proper subset. Is everybody okay with the difference between the two? Any questions?
I have one.
Sure.
So you're saying E can equal itself, but it's not a proper set of itself?
It's not a proper subset because if they're equal, they're not a proper. Up here, if I look and compare set R to set A, R is a subset of A because everything in R is in A. So we can say that those two sets are equal. And if they're equal, it's not a proper subset. If they're equal, it can be a subset, but not a proper subset. That's the difference. In some ways, I compare it to like this symbol and this symbol. I could say that 2 is less than or equal to 2. With that line underneath, it's okay if they're equal. But I can't say that 2 is strictly less than 2. Without that line underneath, they can't be equal.
Oh, okay, I got you.
And so in my mind, the way it works with inequalities is kind of sort of ish the way it works with sets. R can be a subset of A, everything in R is contained in A, but because they're equal, it doesn't work if the little equal sign isn't underneath it. Does that analogy help?
Yeah.
All right. So now we've added to our set definitions and the idea of cardinality, this idea of subsets. And at the end, most of section 2.2 is spent just defining a regular subset as opposed to defining a proper subset. And again, I liken it to that less than or equal. The two sets can only be equal if there's that little equal sign written down below, like with inequalities. The rest of section 2.2 deals with trying to answer the question, how many subsets can a set have? And also, how many of those subsets are proper? And we're going to find that there's a formula that we're going to use to decide how many subsets a set can have and how many proper subsets a set can have. But I'd like to go through and kind of come up with that formula, justify that formula, hopefully in looking at the examples that we're going to look at, it'll help you remember the formula. And so I'm going to look at a whole bunch of sets. And for these sets, I want to look at their cardinality, list all of the possible subsets, count the subsets, and then count the proper subsets. So the first example I want to look at is the empty set. How many things are in the empty set? What's its cardinality? How many elements do I have in there? Is there anything in there? No, so it doesn't have any elements. If I try to list its subsets, I think the only subset it has is itself. And so we can say that it has one subset and no proper subsets. The next set that I want to look at, for lack of originality, I'm going to call set A, and it's going to have the letter A in it. How many elements does my set A have? How many things are in there?
One.
Beautiful. It's got one element. If I list its subsets, well, let's see, we said every set is a subset of itself. And we said that the empty set is a subset of every set. I think those are going to be the only subsets here. So it has two subsets. And of those, how many are proper? Well, if I'm looking at the proper subsets, it can't be equal.
Zero.
You have one proper subset. Everybody with me so far?
No.
No. All right.
You said it can't be zero, but doesn't A equal A?
A equals A. So that's a regular subset. It's equal.
To itself.
And the empty set is also a subset. So we've got two subsets here, but I have to get rid of this one. Only one of them is proper.
So the parentheses one is proper.
Yeah, that is a proper subset. Yeah. Better?
Okay.
Okay. So now let's look at set B, and I'm going to get real creative here. The set's going to contain both A and B. What's the cardinality of set B? How many things are in there?
Two.
Two. Beautiful. If I wanted to list its subsets, if the empty set is a subset of everything, every set is a subset of itself. Can anybody think of another set that would be a subset of this set? Could I have a set that just has A in it? And couldn't I have a set that just has B in it?
Yes.
So how many subsets does this have?
2,
But the set has 2 elements, but let's count down below here. How many subsets do we have?
4.
4 subsets.
4,
And then in order to be proper, it can't be equal to the set itself. So is everybody all right? There are 3 proper.
Yeah.
Yes.
Okay. Be patient. I just want to do this once more. Let's consider the set C. Let's put in it A, B, C. What's the cardinality of set C? How many elements does it have?
3.
Beautiful. So if it's got 3 elements, let's list the subsets. Can anybody name for me any set that would be a subset of this?
AB.
A, B, beautiful. Is there another one?
ABC.
The set itself, beautiful, A, B, C. Any others?
CB.
C, B, beautiful. Any others?
A.
AC,
A, C, beautiful. I think I heard somebody say just A. Any others?
Just B.
Beautiful,
just C,
just C. Great. Any others? What's the subset of everything?
Brackets.
Yeah, just the plain brackets, the empty set. I think that's all. So how many subsets do we have?
8.
8. And of those 8, how many are proper?
7.
Beautiful, because it can't be the set itself. And we could continue all night long doing this, but hopefully that's enough for you folks to notice a pattern. There were no elements. I had 1 subset. When there was 1 element, I had 2 subsets. When there were 2 elements, I had 4 subsets. When there were 3 elements, I had 8 subsets. And for a minute, if I'm going to use my highlighter here, look at these numbers, the number of subsets. What do you notice happens every time I add an element?
It gets doubled.
It gets doubled. And because it gets doubled, that's like saying it gets multiplied by 2, right? Does it make sense that this formula has to involve the number 2 to go along with an idea that the number of subsets doubles every time I add an element? With me so far?
Yes.
And so in general, if S is a set and the cardinality of S is equal to some number, I'm going to call it N, then the formula is that S has 2 to the nth power subsets. And before we go too much further with this formula, and it's not a real difficult formula, it's just 2 to the cardinality, I want to make sure, are you folks all comfortable with exponents? So over here, working backwards, C had 3 elements. And so if I look at 2 to the 3rd, doesn't that mean 2 times 2 times 2? And 2 times 2 times 2 would give me 8. Going up 1, B had 2 elements. If I look at 2 to the cardinality, 2 to the 2nd, is 2 times 2, which is my 4. A has 1 element. And so if I look at 2 to the first, that's just the number 2. And the one I'm not so sure everybody's comfortable with, the empty set has no elements. And has anybody ever seen the idea that any number to the 0 power is always equal to 1? 2 to the 0 is 1. And now I'm frantically looking at my crazy, overly cluttered desk. And what I am not finding is my calculator. So I just want to make sure that everybody's comfortable doing exponents on a calculator. Do you guys all have a calculator with you? Depending on the brand of calculator that you have, if I wanted to, let's say, for example, find something like 2 to the 5th power, if I were a glutton for punishment, I would just go 2 times 2 times 2 times 2 times 2. But on my calculator, I can enter the number 2. And a lot of calculators have a button that looks like it's sort of like an arrow pointing up. It's a caret up. That symbol means exponent. So if I type in 2 caret up 5 and then the equal sign for 2 to the 5th, what are you getting? Anybody got a calculator with them to find that out for me?
32.
Beautiful. If your calculator doesn't have this button with an arrow up, a caret up, it might have a button that looks like either X to the Y, or it could also be Y to the X. And so if your calculator doesn't have that caret up, you're going to press 2 X to the Y 5. And I don't know, some you don't even have to hit the equal, you just need to hit that. Some you do have to hit the equal and you get that 32. Is everybody comfortable with doing this exponent thing on their calculator? Not hearing any complaints. To find the number of subsets, it's 2 to the cardinality. And we got that because it doubled each time. Now for proper subsets, if I had 1 subset, no were proper. If I had 2 subsets, 1 was proper. If I had 4 subsets, 3 was proper. If I had 8 subsets, 7 were proper. Does it make sense to find the number of proper subsets? I'm just subtracting 1. So a set has 2 to the n subsets, and S has that number 2 to the n, and then I'm going to subtract 1 proper subsets. So beyond that, let's look at another example. Let's say D is the set of days of the week. What's the cardinality of D? How many things are in my set of days of the week?
7.
7. And so if I ask how many subsets does D have? We said that formula is 2 to the cardinality. So that would be 2 to the 7th. And so what do you get when you take 2 to the 7th power?
128.
128. And how many are proper?
Maybe.
127.
127, one less. It will always be one less. Let's look at a crazier example. Let's say A is the set of letters of the alphabet. Please, if you're not speaking, could you please mute yourself? There's an awful lot of background noise. What's the cardinality of A? How many letters of the alphabet are there?
26.
26. So if I ask how many subsets does A have? That would be 2 to the 26, which this is one of those ones that I would not want to multiply 2 by itself 26 times. I don't have that level of patience. Does anybody have a calculator with them that can type in 2 to the 26? What are you getting?
I think I got like 67,108,864.
Beautiful. There's 67 million and more subsets.
So how do you figure that out on the calculator again?
Okay. On your calculator, if you could look at the face of it right now, do
Okay.
you have a button that has a little arrow up that looks like that?
Yes.
Okay, so in order to find that, you're going to type in the number 2. Then you're going to hit that arrow up button. Then you're going to type in the number 26. Then you're going to hit the equal sign.
Okay.
Got it?
Yeah, thank you.
Okay, and so could you guys list them all for me? And that was a bad joke. There's no way I would ask you to list 67 million subsets. That's insane. But I might give you on the test a set with 3 or 4 elements to ask you to list all of the subsets. And if you've got to make that list, knowing how many are in it makes it a little bit easier to know if you're done with the list. So of all of those subsets, how many are proper? Well, again, to find the number that are proper, I'm going to just subtract 1 from that answer. So it would be 67,108,863. The number proper is always 1 less. And so this idea of the difference between a regular subset and a proper subset, and using this formula to count how many subsets a set has. Is everybody okay with it?
Yes.
If you're all right with it, believe it or not, we've finished section 2 of chapter 2. This is what's going to be in that second homework, that homework 2.2. Realize in the homework, everything that we just did, the homework is based on, but there are some make you think questions in there. So be careful doing them. I'd like to start looking at section 2.3, but because it's going to kind of be a little bit different conceptually, is everybody all right? Should we take like a 5-minute break before we pick up the next section? Does anybody need to get up and stretch their legs? Has anybody been sitting in front of the Zoom too long? Should we take a 5-minute break or a 10-minute break? I'll leave it up to you guys. How long of a break do you want? You don't care?
No.
Okay, Well, on my computer right now, I have it at 7:27. So let's come back in 8 minutes, somewhere in between. Let's regroup at 7:35. All right?
Okay.
Okay, so let's take a break, and then when we come back, we'll start, yay, drawing pictures. And
All right.
okay, see you guys in a couple minutes. Right. I'm here a little early. As I'm settling back into class, I want to kind of look at the squares and see how many people came in after attendance, because I do believe I let a few people in from the waiting room to make sure that everybody gets noted for being here today. So I'm not seeing an Avery Carpenter. Latanya, I do see. So Latanya, I'm saying that you're here. Let's see. I am not seeing a Spencer. I'm not seeing a Kelly. I'm not seeing Nasla. All right, so I'm going to count those three people: Nasla, Kelly, Spencer, whoops, for and Avery as being absent. All right. All right, I've got that. It's 7:35. Do I have you guys back?
Yep.
Yep. All right, just want to double check. As I was waiting, I went through the names that I saw in the gallery view, and I do not see Avery. I do not see Spencer. I do not see Kelly. Nasla. Are any of the four of you here? Okay, so that's done with attendance for the day. Let's go and then let's continue. Oh my heavens, where is that icon? There, the bright green one. I should be able to see it to share the screen. And the next place that we're going is something that's called a Venn diagram. Has anybody ever heard of a Venn diagram? I guess I was sort of surprised the first semester that I taught this class that a lot of students told me that they had seen Venn diagrams before, but never in a math class. I had a bunch of students tell me that they had used them in something like an English class or a history or social studies class to compare things. When we look at Venn diagrams, they're going to be a diagram used to show the relationship between sets. And before we start drawing a Venn diagram, one more definition, and that's going to be the universal set. The universal set is usually represented by kind of a script, uppercase U, standing for universe, and it's the set of all elements being considered. And when I draw a Venn diagram, I'm always going to start, usually it's a rectangle. I kind of think of it as a box. And that box is going to be my universal set. Which is everything being considered. So if I look at an example, I might have S be the set of students in this class. And that set of students in this class could be considered a part of a larger group. And so here, my universal set could be the set of all students taking classes at the college at N-Trip. And so if I wanted to draw a Venn diagram, my universal set would be all of the students taking classes at the college. And there would be this great big set, a couple thousand students taking classes at the college. And everybody who's in this class, by virtue of being in this class, is also a student at the college. And so I'm going to draw a loop and label it S, and that's going to be the students in this class. And so other sets in the universe are shown as loops. And as I look at this picture, because the students in this class are inside the box, it tells me that the students in this class are all students at the college. And so I can say here that the students in the class is a subset of the universal set, is a subset of the students at the college. And doesn't this picture describe that relation well? As we look at these Venn diagrams, we use them to define some set operations. And set operations are going to be things that we do with sets. Just like things like addition and subtraction are operations on numbers, we'll have some things that are operations on our sets. And the first operation that we're going to talk about is to find the complement of a set. And if S is a set, notation-wise, S with a little, almost like an apostrophe, that's called S prime. And that's the notation, is the complement of the set. And what it stands for, S prime, is a set of all the elements of the universe that are not in the set S. So the complement of a set is everything in the universe that's not in the set. So if I draw a generic Venn diagram with my universal set, and over here in it I have a set, we'll call it S. Everything, inside that loop is in my set S. So everything outside that loop would be the complement of S. So let's construct a Venn diagram for a universal set and a set within it, and decide what the complement will be. So, is everybody okay if I turn the page? For my universal set, thank you. For my universal set, I want to include the numbers from 1 to 10. And let's have S be the set of odd numbers in there. The 1, 3, 5, 7, 9. And before we draw this Venn diagram, we have to say that when we draw a Venn diagram, what we do is you start at the innermost part and work your way out. And so when I draw my diagram, I'm going to always start with this rectangle, this box. And this box is the universal set. It's going to contain everything. My set S is going to be a subset of my universal set. That's the way it's defined. I'm going to label this S. Now, when I fill in my Venn diagram, we want to start on the inside. And the innermost part is this set S. So inside of S, I'm going to put my 1, 3, 5, 7, 9. It doesn't really matter where you put them when you're drawing it by hand, as long as they're in that loop. When we're putting them in that loop, if you're drawing it by hand, you should be able to space them out in such a way that you don't really need to show any commas or anything like that. Looking at this diagram, does everybody see, not looking at the stuff up above, but looking at the picture, that inside of S, I have 1, 3, 5, 7, and 9. But because the 1, 3, 5, 7, and 9 are inside S, and S is inside U, the universe, do you see how I've already shown that those numbers, 1, 3, 5, 7, and 9, are also in my universe? And again, when I show what's in a set, I don't list them more than once. Those numbers are in my universal set. There's no need to list them again. However, there's some more things in the universal set besides what's in S. In my universal set, there's 1, it's in there already. I have to add 2, 3 is in there already. I have to add 4, 5 is in there already. I have to add 6, 7's in there already. I have to add 8, 9's in there already. I have to add 10. And so do you see, looking at this Venn diagram, my universe, my box contains all of the numbers from 1 through 10, but my set S only contains the 1, 3, 5, 7, and 9. And so you might be asked, what's S complement? And again, when I see that S with an apostrophe, that means the complement of S. And it's just a fancy way of saying, okay, so what's outside of S? And again, I'm only restricting my thinking to this universe, this world that we've defined in the box. And what's in my universe that's outside of S, not in my loop? Well, that would be my 2, 4, 6, 8, and 10. So far, so good. And so if I only have one set in my Venn diagram, I'm only going to have that one loop in there. Instead, if I want to show the relationship between two sets in a Venn diagram, well, I'm going to have my universal set. And I guess if I wanted to, I could put two sets in there. One set, two set. But I don't really like that picture because this would only work if they had no elements in common. And if anybody's interested, that idea of two sets having no elements in common would be disjoint. disjoint sets have no elements in common. But that Venn diagram would only cover that specific case. I guess if I wanted to, I could draw my set S, and then I might have my set T on the inside, but that wouldn't really be general enough because this would only work if T is a subset of S. And if T is a subset of S, I could really just draw T inside S. But again, we're not going to use that drawing because sometimes we might have disjoint sets and sometimes the sets might have something in common, but one might not be fully contained in the other. Instead, the one that we're going to use is going to be, if this is my universal set, and this is my first set S, I'm going to draw my second set T like this, and I'm going to have some overlap. And this diagram is going to be able to be used if they have some elements in common. This diagram is going to be able to be used if they have no elements in common. And this diagram is going to be able to be used if they have, if one is the subset of the other. Before we get too much further into that, as I look at this picture, do you see that this diagram, a Venn diagram for two sets in my universe has, we're going to say it has 4 regions. Mr. Blitzer, the author of the textbook, labels them with Roman numerals. So let's first make sure everybody's all right with their Roman numerals. 1, 2, 3, 4. Is everybody familiar with those Roman numerals? Usually, with this generic 2-set Venn diagram, 1 is over here, 2 is the overlap, 3 is over here, and the rest of my universal set is 4. And if I were to try to describe them, does everybody see that region 1 would be the elements that are only in S? Region 2 will be the elements common to both S and T. Region 3 will be the elements that are only in T. And region 4 will be all of the elements of the universe that are outside of both S and T. So, using those regions, using those definitions, I'd like to draw a Venn diagram for two sets. Does everybody have all of this down? Is it okay if I turn the page, or do you guys want me to wait a minute?
Nope, I'm good.
I'm all right.
Okay, then turning the page, let's say our universal set this time just contains the numbers 1 through 9. Let's say I have a set A that contains the odds 1, 3, 5, 7, 9. Whoops. Every once in a while, this stylus and I don't get along. And let's say set B contains the multiples of 3, 3, 6, 9. And I want to draw a Venn diagram. When I draw a Venn diagram, I start with my universal set, my box. I'll label that U. Does everybody see I've got two separate sets inside my universe? And so I'm going to draw my two loops. And especially if you're drawing them by hand, it's important that you name them. One will name A, the other will name B. Now again, we said we're going to start at the innermost part and work our way out. And so the innermost part over here would be where A and B overlap. And where A and B overlap is going to be inside of A and inside of B. So I want to compare sets A and B and ask, what do they have in common?
Would that be 3 and 9?
3 and 9. Beautiful. And so in the overlap, I'll put what they have in common. Because they're in that region, they're already in loop A and they're already in loop B. Now I'm going to work my way out. And so now I want to finish the rest of A. A already has 3 and 9 in it, but shouldn't I also add the 1, 5, and 7? Then I want to look at loop B. Does everybody see loop B already has a 3 and 9 in it, but B contains 3, 6, and 9. So I'm going to put 6 in that other region of B. And then lastly, I've got to make sure I have my whole universal set. Inside my universal set, I've got 1. I have to add 2, but it's outside of either, so I'll put it in that other region. I have 3. I need to add 4. I have 5. I have 6. I have 7. I need to add 8. And I have 9. And so do you see how that shows me the relationship between the two sets? If we had started with the picture, could everybody go back and say, oh yeah, A contains 1, 3, 5, 7, 9? Could everybody look at the picture and say, okay, inside the loop for B, I've got 3, 6, and 9? And then could everybody look at the picture and say, okay, the universal set has 2, 4, 8, 1, 5, 7, 3, 9, and 6. Again, order doesn't matter. If you wanted to, you could just number 1 through 9, but they're all in there. And see how this diagram kind of shows the relationships between the sets. Now, when I spoke at the beginning, students told me that in English class, they had used diagrams like this if, for example, they were comparing two different characters in a book. And they would have to list in this middle the traits that they had in common. And in here, the traits that's only one character has or the other. Have you guys seen this type of diagram before? Used to compare two things. What do they have in common? What do they have that's different? And what are all of the features that I'm looking at in this world I'm considering? This okay, guys?
Yep.
Great.
Seen it before, but haven't not for writing or anything.
Okay. But you've seen it used to compare two things. From this picture, I'm going to define my next set operation. And my next set operation is going to be the intersection of two sets. When I talk about the intersection of two sets, the notation for intersection is this kind of funny looking elongated upside down U, so that this symbol means the intersection. Now, not gonna lie, I think I told you guys earlier, I sometimes reason like a child. And so when I put on my little kid cap, is there anybody else, when they hear the word intersection, you think of where two streets cross? And I live near the intersection of two kind of busy streets. I live real near the intersection of Main Street and Harlem Road in Amherst. Is anybody familiar with that intersection of Main and Harlem?
Yeah.
Yeah. Okay, so you know my neighborhood. And so sometimes I'm crazy and I wake up super early in the morning before there's any traffic. And when I wake up early in the morning, sometimes I go for a run. And so I'm running, and if I'm running down Main Street, if I'm over here, I'm in Main Street. And if I'm running down Harlem Road, if I'm over here, I'm in Harlem. But if I'm standing right here on this piece of pavement, isn't this pavement part of Main Street if I'm going from east to west? And isn't this piece of pavement part of Harlem Road if I'm going from north to south? And so that intersection, isn't that the overlap or the pavement that's common to both? And that's what I'm looking for when I'm looking for the intersection of two sets. I'm going to say that if A and B are two sets, A intersect B, which I'm going to write A with that funny upside down U, B, A intersect B is a set. So when I take the intersection of two sets, I should get a set. And it's the set of elements that are common to both sets. It's where the two sets overlap. It's the stuff that's in both of them. And so if I look at my generic two-set Venn diagram, I've got my set A, I've got my set B, and over here, that's where they overlap. What's in there would be A intersect B. And so, are you guys all right if I just scroll up to the preceding example where my universal set was 1 through 9? My set A were the odd numbers. My set B were the multiples of 3. And if I wanted to know what was in the set A intersect B, again, it's a set. So I'm going to use my braces. I have to use my set notation. And if I compare set A and set B, here looking at their rosters, we had said before what they have in common are the numbers 3 and 9. And if I go back to my Venn diagram, isn't that what was in the overlap? That overlap is my A intersect B. And so I'm going to take a minute to redraw that Venn diagram with those elements in it, because I want to ask a few more questions about those sets. If you can fit it all on one page without scrolling up and down, don't feel the need to redraw it. But I don't want to get seasick bouncing up and down, so I am going to redraw it. My intersect is 3, 9. B also needs 6. A also needs 1, 5, 7. And the universal set needs 2, not you, 2, 4, and 8. And I think that replicates what we had before. And so from this diagram, in addition from the rosters, can everybody see? I almost think it's easier to find this one in the picture. A intersect B is what's in the overlap. But now I'm going to get some tricky questions for you. What's a complement? What's outside of A in my Venn diagram? You can get it in one of two ways. We can compare the rosters, and comparing the rosters, we can think of crossing out what's in A and seeing what's left over. Or with these, sometimes I think colored pens are worth their weight in gold. If A is what's inside the red circle, wouldn't A complement be everything outside the red circle? Or my 2, 4, 6, 8. Then, what if I ask for B complement? B complement, well, if B is 3, 6, 9, I could look at everything inside the universal set after I cross out 3, the 6, and the 9. Or I could look at my Venn diagram, and I'm going to use the color blue to show set B, and it would be everything outside of the blue circle. Does anybody want to volunteer for me what you would put inside that set B complement?
1, 2, 4, 5, 7, and 8.
So we've removed the 3, 6, and 9. Everybody okay with that?
Yes.
But sometimes the homework's going to ask you to get a little bit more involved than that. What if I asked for A complement intersect B complement? Well, for A complement intersect B complement, I want to compare these two. What do those two complements have in common? Well, if I compare the rosters, they both have
2,
good
4, and 8.
2, 4, and 8. So can everybody get that by comparing the rosters? If I look at the Venn diagram, I'm saying what's outside of A and also outside of B. And you see what's outside of both of them is indeed that 2, 4, and 8. Now I'm going to do one more operation on this diagram before we define our next operation. And I want to look at A intersect B, which we did already. A intersect B, we said was the 3 and 9. But now I want to take the complement of that. And before I do this, is everybody familiar with the idea in math? If I've got parentheses, I got to do what's inside the parentheses first. And so again, A intersect B, we said, was the 3 and 9. And so I want the complement of 3 and 9, or I want everything except 3 and 9. Or looking at the Venn diagram, if the intersection is what I'm highlighting in yellow, wouldn't the complement be everything but that? Everything outside the overlap. So what do you get for the A intersect B complement? Anybody?
Got 1, 2, 4, 5, 6, 7, 8.
Beautiful. And if you want to name them in order, great. But again, realize with sets that the order doesn't matter. So if you wanted to put them in a different order, you're more than welcome to do so. So before we define that next operation, actually, what time do we have? Let's define that next operation. And then let's look at some more examples. The next operation that we're going to have for sets is the union of two sets. And I know that my penmanship is kind of sort of ish sucky, but whenever I look at my universal set, I try to make it that cursive looking U, because the notation for the union of two sets is a great big kind of blocky looking elongated U. And so this symbol means union. And if you look at it, do you notice that the union symbol is like the intersection symbol upside down? Not so much Mr. Blitzer in your class, text, pardon me, but one of the other classes that I teach that goes over a little bit, not the same depth as we are, but a little bit of sets, calls the symbol for union a cup and the symbol for intersection a cap. And so to me, the cap kind of looks like a knit hat. And I guess the cup sort of looks like a cup, but it looks like it would be a wiggly wobbly cup. We have a flat base. And so we're going to say that if A and B are two sets, A union B is going to be written A union B is the set that contains all the elements from both sets. And so in a past life, I was once an organizer. And when I was an organizer, we worked an awful lot with labor unions. And when I see that word union, the first thing that comes to my mind is the labor union. And in a labor union, you want everybody in the union because there's strength in numbers. So when you're taking the union, you're taking everybody. When I posed this idea to students a few years ago, instead they told me that when they think of a union, they think of something like a civil union or a marriage. And taking that idea that when we look at the union of two sets, it's like a marriage. Has anybody ever seen a program for a wedding where they have this lovely little diagram on the front and it's supposed to be overlapping wedding rings? But gosh darn it all, doesn't it look like a Venn diagram? And if I think about the idea of a marriage, if I think about the idea of the union in a marriage, doesn't it include all of the first partner's stuff? Doesn't it include all of the second partner's stuff? And then if they were hanging out for a while before they got married, doesn't it include all of the stuff that they got together? And so when I look at the union of two sets, I'm including everything from both of them. And so going from a wedding program to a Venn diagram, that's my universal set. If this is set A and this is set B, when I take the union of the two sets, I'm taking everything, absolutely everything that's in both of them. And so if I go back, and again, I'm going to recreate that same Venn diagram. I'm sorry, I'm beating this example to death. My universal set was 1 through 9. My set A were the odds, the 1, 3, 5, 7, 9. My set B were the multiples of 3, the 3, 6, 9. And here, if I look for a union B, I'm taking everything outside of, I'm sorry, I'm taking everything inside of A. So when I look at the union, I want to see everything in A. 1, 3, 5, 7, 9. And I want to see everything in B. 3, but it's in there already. 6, I've got to add. And 9 is in there already. When I look at finding the union, I also almost think of it making a grocery list. If I have 2 recipes and I want to make a list of what I need to buy when I go to the grocery store, if the 2 recipes have the same ingredient, that still is only going to show up once on my grocery list, right? If recipe A needs onions and recipe B needs onions, I'm only going to put onions on my list once. And so it's everything from both. And again, recreating that Venn diagram. This was the 3, 9. Over here, I had the 6. Here, I had the 1, 5, 7. Here, I had the 2, 4, 8. And again, the union, if instead of having the roster, I was looking at the Venn diagram. Is everybody all right? The Venn diagram is everything from both sets. And so, what if I ask for A union B inside parentheses, complement?
2, 4, 8.
Beautiful. And then let's get a little tricky. Let's look for A complement, union B complement. And so A complement, again, was outside of A. And so outside of A, we have our 2, 4, 6, 8. B complement was outside of B. And outside of B, we have the 1, 5, 7, and the 2, 4, and 8 are in there already. And so I'm taking what's outside of A and combining it with what's outside of B. How cool is that? So let's look at one example that kind of asks us to do it all. And then let's call it a night. Can I turn the page on this to get to that next example?
Yeah.
So this time for my universal set, let me have, let's use letters instead. A, B, C, D, E, F, G. Let's have my set A be the vowels A, E. And let's have my set B be, let's have it be the first 3 letters. Oh, the first 4 letters, A, B, C, D. I'm going to ask you to, first of all, draw a Venn diagram. And so I'm going to shut up for a minute and ask you folks to first finish the picture. And I'll help just to say that the box is the universal set. And I'll have 2 loops. And one will be the loop for A, and the other will be the loop for B. And please let me know when you're finished drawing the picture, filling it in. Oh, I forgot to put a comma in between my F and G. That's good.
Done.
How about everybody else? Are you all done, or do you want me to hold my horses for a minute?
I'm done.
I'm done.
So did everybody start? What A and B have in common is just the lowercase a. Set A also needs the letter E. Set B also needs the letters B, C, D. And in my universal set, I also need the F and the G. A, B, C, D, E, F, G, got them all. Does everybody have a diagram that looks something like that?
Yes.
Okay, so now I'm going to give you a list of things to find. You can either use the roster or the diagram, totally up to you. I want A complement. I want B complement. I want A intersect B. I want A union B. I want A complement intersect B complement. I want A intersect B complement. Then I want A intersect the empty set. And I want B union the empty set. Does that look like enough for starters? And I'm going to shut up and ask you guys to do that. I'll give you a couple minutes.
Done.
How about everybody else? Does everybody else want more time or do you want to start going over?
Ready.
Everybody okay if I get started?
Yes.
Yes.
Yeah.
A complement outside of A. If I look at the loops, A has A and E in it. Outside would be B, C, D, F, G. How did everybody do with that one?
Good.
Great. B complement is outside of B, except B contains A, B, C, D. Outside of it would be my E, F, G. And again, they're sets. And so put the braces, but again, the braces don't have to look pretty. Some of mine are nastier than anything, but they're braces, not parentheses. And it's important to put those commas in between. I apologize for missing a comma at the beginning. How did everybody do with B complement?
Muy bien.
Grand. A intersect B is the overlap, and the only thing that they share is A. A union B is everything in the loops. Again, the little kid in me calls this diagram, to me, it looks like a sideways snowman. So everything inside the snowman would be E, A, B, C, D. And I'm taking them from the diagram as I look at them from left to right. If you wanted to, you could put them in order. A, B, C, D, E. Again, order doesn't matter. The next ones are a little bit more difficult. A complement intersect B complement. Well, that's taking these two sets on the left and saying, what do they have in common? And so if I look to see what the two complements have in common, it looks like they both have F and G. Again, it's a set, so put it in braces. Or I could say outside of A, in common with outside of B, outside of both would be F and G. Next, A intersect B complement. Well, A intersect B is over here on the left. A intersect B is just A. When I take the complement of the A, the rest of the universe would be my B, C, D, E, F, G. Or if I'm looking at my Venn diagram, the intersection is this part I highlighted in yellow. The complement of that is everything else. Next one asks, what does A have in common with the empty set? Well, if I compare A with the set that has nothing, that set's got nothing in it. So the only thing that it can have in common is nothing. And then if I take the set B and union it with the empty set, well, B, it's got to have everything in B. So that's A, B, C, D. And now if I add everything in the empty set, yeah, there's nothing to add. And so when I look at B union the empty set, I just get my set B back. And isn't that kind of almost like when you add 0 to something, it doesn't change it. So there you go. How'd you guys do?
Terrible.
Terrible. All right, we need to backtrack and add detail to any of this. Did you want to go over any of the parts again? I'm going to stop for a second and go to the list at the beginning of class. Homeworks 1 and 2, that's what's due next week. Homeworks 1 and 2 include my set definitions, my cardinality, and my subsets, both regular and proper. Homework 3 is what we're doing right now. Homework 3 are the Venn diagrams, the complement, the union, and the intersection. So complete homework 1 and 2. If you have questions, bring those to class next Tuesday. And again, we'll be meeting in campus on Tuesday. The homework isn't really due until Wednesday. But also, especially if this was a little challenging to you, this last example, try to get a good start on homework 3. If you have problems, use the help functions. Send me an email. Come to the office hour. Don't get frustrated, whatever you do. Don't ever get frustrated with math. Send me an email, ask for help before you get frustrated. And ask questions at the beginning of next class. I promise we won't go any further until everybody's comfortable with their homework. So I'm looking and we've kind of sort of got to the end of time. Does anybody, I'm going to stop recording. Does anybody have